Hi, guys, and welcome back to the Uncast. As always, I'm your host, Jonathan Panozzo, and today I wanted to spend a little time talking more about hardware and specking out your own Unraid system. Now, we get tons of questions about hardware all the time, most of them framed to ask our opinion of what the quote-unquote best hardware is for Unraid nowadays. But answering that question can be very tricky, as it really depends on your budget and how you intend to use it. So in this episode, I'm going to walk you through how I guide my friends and family through picking their hardware to use with Unraid. So first and foremost, let's start with whether to build your own or buy a pre-built system. For me, this all comes down to whether this is a business use case and whether or not you're comfortable in building your own computers. So business customers, generally speaking, should really never build their own hardware. Okay, I'm going to get some flack from a handful of people about this, but I stand by that statement, and that's because these users tend to prioritize a lot of things over cost when making purchases. Reliability, scalability, maintenance, serviceability. These are the main drivers for a lot of business customers that are buying a server. They basically want a box that they can put in their server closet for a long period of time, maybe upwards of 5 years, and rarely touch it after the initial setup. They don't care about GPU pass-through, they don't care about gaming, they don't even care about most of the Docker containers. What they're going to care about most is how much data they can throw at it and who they can call if something breaks. And for these types of users, I tend to lean towards pre-built options from vendors with solid hardware replacement plans, such as 45 drives, HP, Dell. You guys know the suspects, right? The usual suspects. I also recommend they try to get the most standard host bus adapter storage controllers that they can, no hardware-based RAID controllers, if possible. And I always think of it as, what can I tell them to buy that is going to be pre-configured and easy to handle when stuff goes wrong? Now, you're going to pay a huge premium for that in support and warranty, but you're going to have a streamlined experience. Now, for smaller customers that still prioritize serviceability or individuals that don't know how to build their own PC, you can go with pre-built options from other companies that don't offer that same level of warranty service if you're willing to accept that. But there's a lesson that you learn, and it's that good, fast, and cheap. You can pick two of those three. You never get all three. It just won't happen. So yeah, generally speaking, a pre-built system is going to cost more than building it yourself. But sometimes, with component availability, that isn't the case. Like there's time periods where, like, if the GPUs are going for 2x or 3x market value on eBay and whatnot, because they're all sold out everywhere, but you can find a vendor that offers a pre-built system that includes that GPU. The vendor's less likely to do that market price gouging than somebody who's just buying one from Best Buy and then turning it online for a profit. Okay, so now that we've addressed kind of the pre-built versus the do-it-yourself debate, I think the rest of this discussion is going to be about component selection, which is applicable regardless of a pre-built or a do-it-yourself system. So the first big decision is your CPU vendor, Intel or AMD. Now, as someone who's owned plenty from both vendors on CPUs and GPUs, I'm not going to try and convince anyone that one brand is higher quality than the other. The battle between AMD users and Intel users has been fueled even longer than the console versus PC gaming war, and nothing I'm going to say today is going to change any of that. So instead, I actually want to focus on the facts about both platforms and highlight their respective strengths and weaknesses. So let's start about grouped components. We should talk about that. So most modern-day Intel-based systems feature an Intel CPU, an Intel integrated graphics device that's frankly a function of the CPU, an Intel-based network interface, usually a 1 gigabit, sometimes 10, an Intel-based USB controller, and an Intel-based storage controller. This means that Intel is building essentially all of the critical components and building them into the motherboard themselves, so that the user doesn't have to rely on support from multiple vendors. And if there's a problem in one stack that affects another, Intel has multiple approaches that they can take to solving that problem. With AMD-based systems, most require a mishmash of various vendor components beyond their CPU and integrated GPU. So AMD does provide a built-in GPU for some systems, and it's based on Radeon, but it is not soldered onto the CPU. The network interface card is typically from Realtek, and most of the time the storage controller is from Marvell, although I recently saw a newer Ryzen system that one of our friends had, which featured what looked like was an AMD storage controller, so maybe they're getting away from that. But generally speaking, Realtek is notorious for having issues from Linux kernel to Linux kernel, as they don't always stay in lockstep with the kernel, and performance issues can arise as a result. Marvell had a number of issues with IOMMU groups, specifically affecting passing through PCIe devices like graphics cards to virtual machines. So there's just a handful of different problems that can occur with these specific devices. And again, if you were the manufacturer, right? If you're AMD, your priority is to support the largest use case with a quality product. And what is the number one use case for people that are building their own hardware? Windows. I mean, it's just been that way for the longest time, and it's going to continue to be that way for a long time. So you don't see as much focus on testing and support with Linux as you do with Windows, specifically on those platforms. So it's for those reasons that we tend to see more issues that are Linux specific when you're using that hardware. Now, there are plenty of users in our community that use these kinds of AMD systems, and they don't have issues, but some do. And when they do, there's a lot of finger pointing that can occur between the various vendor components that are in play. It just creates frustration from a support perspective that doesn't seem to plague Intel as often. Okay, but the next thing we should talk about, aside from these grouped components, is price for performance. And this is where AMD blows the pants off of Intel, because generally speaking, AMD CPUs feature more logical CPUs per dollar than their Intel counterparts. So if you have high performance applications that are multi-threaded, they can take full advantage of all the horsepower that AMD processors can provide. And while Intel does offer high core count CPUs, they come at a much steeper price point than AMD, so you're definitely paying a premium for the blue brand. The last thing to mention about AMD versus Intel is GPU pass-through. I'm not going to beat a dead horse here because I've said it before, but I'll say it one last time. Generally speaking, Intel users that leverage an NVIDIA GPU have far greater success at passing that GPU through to a VM than AMD users, even when the AMD CPU user is using an NVIDIA GPU. This isn't always the case, but issues arise far more frequently with AMD systems than they do with Intel. That's all I'm going to say on it. So which should you choose? Well, generally speaking, I always recommend, I tend to lean towards recommending Intel to my friends and family, because I know that no matter how their use cases may change over time, all the functionality is going to work. But if I'm talking to my more technically savvy friends that are willing to accept any potential limitations or gotchas, I guide them towards AMD. And when they tell me, specifically when they tell me that PCIe pass-through isn't on their to-do list. And if you're building a box primarily for headless VMs, Docker containers, and storage, AMD can offer you more for your money than Intel. And I should also mention that while I have used both AMD and Intel platforms, in the more recent years, probably the last 5 to 8 years, I have been almost exclusively Intel. So I know that AMD is making huge strides. I know that Ryzen has had a huge impact. And one of our good friends, Nick, if you're out there and listening, I love you, brother. He built a new Ryzen-based system. And I got to tell you, the thing is just amazing. It works amazing. Even with GPU pass-through, it works amazing. Like, it actually had me kind of questioning my next build. So, I'm not going to say that AMD is better than Intel or that Intel's better than AMD. I'm just going to say that this is my knowledge, this is my experiences, this is what I've seen from our community, and that's really all there is to it. Okay, so now I want to shift the discussion to how beefy the hardware should be, because this is probably one of the hardest questions to answer, because it really does all come down to the applications and the virtual machines that you're going to use. So if we're talking about a basic storage appliance here, Unraid's core feature of providing dedicated storage has incredibly low impact to the CPU. In fact, one of the main reasons we grew as a company was our ability to convince users to take their old PC that they just replaced with newer hardware and use it as a dedicated storage appliance. Most of the time, those old PCs, they got tossed into the boneyard, aka basement, and they'd sit there until the next time you moved houses, at which point you would most likely toss them. The wife's just looking at you like, can you just throw that thing away? There's no reason to keep holding on to that. And you're like, well, maybe I was going to use it for something. But, at that point, you do tend to throw it away. But for us, that was a great way to get somebody started with Unraid. Hey, man, you got a good old box there? Just take it and put Unraid on it. Use it as a dedicated storage appliance. It was a good use case. So if you're doing nothing with Unraid except basic storage, so no apps, no VMs, Even a lowly single or dual core processor is enough. But if you intend to run applications on the box, things do get more complicated. And performance requirements for applications can vary widely. So to simplify, let's think about them in terms of real-time applications versus non-real-time applications. All right, what does that mean, right? So an example of a real-time application would be when someone is watching content from a media server where transcoding is required. The request to watch the content isn't queued in advance, but rather the user clicks play, and they expect the content to play as quickly as it is able. An example of a non-real-time application would be any of the downloaders used to acquire the content. Those applications are running in the background. They're constantly searching, finding, and pulling down that content in an automatic fashion. The difference between these use cases is the expectation of performance and the user experience. So if you supply low resources to the media server application, it can result in an absolutely horrible user experience plagued with buffering issues. But if you supply low resources to the content downloaders, they won't stop working. They may slow down slightly, but as these tasks are happening in the background, the lower performance doesn't lead to a subpar user experience. You know, most people set these things up, go to sleep, and the next morning they got a whole bunch of stuff new on their system. It didn't matter whether it took 8 hours or 9 hours because they were sleeping through all of it anyway. So that's the big difference between real-time and non-real-time applications. Now with virtual machines, things get a little bit more complicated still. If you're running VMs as headless servers for applications that aren't available as Docker containers, your performance requirements are solely going to tie back to the underlying application. So you're going to need to look at that vendor's docs and see what they require, and maybe buffer that a little bit if you're going to be adding other apps alongside of it. Okay. Now, if you're running VMs for gaming or other local desktop performance needs, once again, the plot thickens. So real-time performance VMs are going to be just like their real-time performance application counterparts, but with one big caveat: they require even more isolated control over resources than their containers, or than containers. A gaming VM is the most demanding use case for an Unraid server, and that's because it requires physical CPU cores to be pinned specifically to the VM and isolated from any other uses on the system, even when the VM is powered down. That's an important distinction, okay? And it is for those reasons that if you're going with a gaming VM, you should oversize your CPU and memory to accommodate for this. So generally speaking, I like to see between 6 and 8 logical CPUs assigned to the gaming VM with no less than 16 gigs of mem. You can get away with less if you're playing far less intensive games, but for modern stuff, you just don't want to feel a bottleneck. In addition, games, unlike server applications, are more about clock speed than core count. So while your CPU might have a ton of cores, if the clock speed is low, that can have an effect on your frame rate. So what am I saying? Well, if you put a gun in my head, what am I recommending? Well, I'd say stick with Intel i7 or i9 CPUs for any gaming use cases, and then a minimum of 32 gigs of RAM for the host. So when I said 16 earlier, I was referring to how much you were going to assign to your guest, to your Windows instance, but the host, you want to have probably about 32 gigs of RAM. And the reason for this is that you're going to assign at least 16 to your Windows VM, right? But then there's a chunk of additional memory that gets kind of reserved when you start the VM that's for the overhead associated with emulation. So you can't just base it on, well, I'm going to have 16 for Unraid and I'm going to have 16 for my gaming VM. It's more like you're going to have 16 for your gaming VM and then maybe another 4 to 8 in overhead for that VM. And that might be a stretch. That might be a little bit more than it really is. And then the rest is for the host and whatever other applications you're running. So the problem with going too low end, like I've seen some people try to build gaming rigs with i5s, like virtual gaming rigs with like i5s or like really old i7s, is that if you give insufficient performance to the VM, and you're going to see the same impact as if it was bare metal. You're going to have lower frame rates, and you might end up having to lower the overall quality of graphics for the game being played. And since we're on the subject of talking about gaming VMs, let's shift hardware discussion for a minute to GPUs. So I'm not going to spend long on this. It's going to be a less than 1 minute discussion because I've already talked about it in the past. As I've mentioned before, I'm not a fan of how AMD GPUs work with pass-through. Some users get it to work, and that's great, but I found them to be far more problematic than NVIDIA, so I can't yet recommend them. As far as what kind to get, if it's strictly for gaming, NVIDIA's GTX and RTX class devices work perfectly fine, And because VFIO works as well as it does for passing through these devices, you can pretty much size up your GPU needs the same way you would for a bare metal configuration. It's based upon the games that you want to play. So there's no, I don't want to say there's very little, if any, GPU overhead associated with passing that GPU through to a VM. You shouldn't even consider it. So just worry about the games that you're looking to play and what those requirements are and size your GPU accordingly. All right, not much else to say there, so let's move on. Let's talk about RAM. A lot of time, the focus on RAM tends to be about storage performance, believe it or not. This is not specific to Unraid, but in general, when people talk about RAM for servers, they tend to talk about storage performance, which is kind of weird because it's not really all that RAM bound. So when a user writes data to a share, the data is initially cached in RAM and then written to a disk. So it makes people think they need more RAM in order to get better storage performance, but that's rarely the case with Unraid. Generally speaking, we recommend about 4 gigs of RAM to give you enough room to run the OS and a few plugins, but if you're going to be adding other applications, you're going to need more memory. One of the big differences, though, and this is an important one to understand in terms of sizing your RAM requirements, is the differences between apps running in containers and virtual machines, and that's in how memory gets reserved and utilized. So containers run just like another application on the same system. They share resources with the host and can only pull on memory when they actually need it. VMs, however, require you to assign a chunk of memory to them when they boot up, forcing you to leave that memory reserved to them alone, regardless if they actively need it or not. So let's say you have Plex running in a container and a VM running with the Windows version of Plex inside of it. What would be the difference? When the Windows VM boots up, it's assigned a chunk of memory that you decide. So let's say you pick 4 gigs. That means as soon as it starts up, that 4 gigs of memory, plus a little extra for emulation, is immediately pulled away from the host and cannot be used for any other functions until that VM is shut down. With Plex running as a Docker container, it only pulls memory as it's needed. And at the start of the application, it needs a small amount of memory to get going. And once it's running in idle, it won't need any more until someone starts interacting with it, watching a movie, adding a library, etc. So the net difference upon starting the application in terms of memory consumption as a container, we're talking measurable in megabytes. As a VM, 4 gigs. It's 4 gigs because you need all 4 gigs of memory to be reserved for Windows. And by the way, Plex doesn't even get all of that 4 gigs because Windows is going to take up a huge chunk, and the other services that Windows is running is going to take up a chunk. So Plex is just getting a subset of a subset in that instance, right? That's why for applications like Plex, it's more ideal to run them as a container. So, and because it's in a container, another big difference is not just the upfront requirements, but it's the upper limit in terms of how much memory the app can grab. So with it running as a container, you can set a limit. There's a parameter you can pass through to Docker, to the container specifically, to limit how much total RAM that container is allowed to grab. So if you have another application running that's very memory intensive and you're like, hey, I always need to make sure there's at least this much memory reserved for that app, and I don't want Plex to steal from it, you can go back to Plex and say, you know what, I'm going to set a limit. I'm going to cap you at X gigabytes of RAM, and you're not allowed to consume any more than that. Okay, you can do that with Docker. But if you don't set a limit, Plex can grab as much as it needs. It's free to grow and shrink its RAM needs as necessary. But within a VM, because the VM was started with only 4 gigs of memory assigned, it's limited to those 4 gigs of memory. Now, caveats, there are ways to technically add memory to a running VM or allow for what's called memory ballooning, but we're not even going to go down that road at this point because, quite frankly, that's more for when one VM and another VM need to be able to have more memory assigned to them in aggregate than the host has. It's called memory oversubscription, and it's a totally different use case. So we're not even going to get into that right now. Just know that for everything we're talking about, whatever memory you assign to the VM, that's what the VM's stuck with until you shut it down, change that number, and start it up again. So generally speaking, VMs are just going to be more resource heavy than containers, which means sizing them accurately before you buy your hardware is very, very key. Okay, now I want to shift the discussion to storage. Okay, I know that seems weird that as a storage-based product, storage is only coming up so late in the discussion, but the reality is it's one of the easier things to kind of figure out And there's not really much to recommend. It's more about personal preference, right? So recommending individual devices isn't something that we're going to do, as vendor positions in the market can change over time. And to us, honestly, a SATA disk is a SATA disk, regardless of the brand. So instead of focusing on recommending like Seagate versus Western Digital, let's focus on sizing. How much storage should you really add? So the first thing you need to do is assess how much data you already have that you would immediately load onto the system. So you can do that if you already have an existing server of some type. That's pretty easy to do. If you don't, I would recommend looking at things like if you're an Android user, look at Google Photos and all the content that you've been creating there. My Android device decided to listen to me when I said that. Or if you're an Apple user, you can go on iCloud and see how much data you've got over there. If you are planning on doing different things after you build your Unraid server that are going to add even more data, for example, backing up other devices, now you got to think about that as well. So if you've got multiple Windows devices or Mac devices on the network and you want to back those up to your Unraid server, how many gigabytes per device are you expecting and over what period? Another thing to consider is whether or not you are adding VMs to the system, and if so, how many virtual disks per virtual machine, and of what size, and do you anticipate them growing over time? Now, all these questions will ultimately drive you insane at trying to predict, because it's hard. It's just really hard to predict your data growth. So you just got to do the best you can and buffer a lot of room. The worst thing that you can do is completely undersize your system and find yourself replacing, not adding devices later on. So here's some general recommendations. For the array, you're going to want at least one parity disk to protect your array for up to, I would say, 8 devices. If you're going to go beyond 8, I think having dual parity makes a lot more sense. This is especially true as the size of devices increases. So the likelihood of multiple successive disk failures occurring increases as you increase the width of the array. The more devices, the more the risk. I just got a question the other day in support saying, why do you guys only have 30 devices in the array? Why can't I have 100? Well, it would not be very responsible of us as a storage vendor to tell people, yeah, that's a totally safe thing to do. And then all of a sudden, somebody has a disk failure. They go to do a replacement. And in the middle of that replacement, one of the other 99 disks in the system fails. Well, with dual parity, you're okay. But then during that rebuild, one of the 98 other devices in the system fails. Now you've had permanent data loss. So there is a point at which you don't want to grow wider in the array, because the likelihood of those multiple failures occurring grows. And that is especially even more true as the individual sizes of devices increases as well. That means the rebuild time is getting longer and longer. So the time it would take to rebuild a 4 terabyte drive, for example, in an array of nothing but 4 terabyte drives, it's going to be far faster than an array that's filled with 16 terabyte drives, right? And it's just because now you've got more sectors on the disk that you have to scan through. So yeah, at the end of the day, if you're going 8 or under, a single parity disk is fine. You're more than welcome to have 2. If you only have 6 storage devices, for example, and you want 2 of those to be parity, hey, if that's important, if you're like, redundancy is the number one thing on my list, okay, fine, go for it. But if you're asking me for my recommendation, I usually say 8 and under 1, 9 and over 2 for parity specifically. The other question that I get a lot is, should I buy smaller quantities of bigger drives or bigger quantities of smaller drives? And I actually lean towards the former. So even going off of what I was just saying about parity and array width and how long it takes to do rebuilds, even that being said, I still think it makes more sense to go bigger size and lower quantity. And the reason is that you only have so many ports on the motherboard to work with. And if you're buying more devices in quantity because you're choosing to buy smaller in size, you could be putting yourself in a situation where later expansion becomes more difficult. And now you either have to add another storage controller, change the case for the system that you're using to accommodate the additional devices, or something else. So just give yourself some room. And make sure you leave some ports open for the cache pool as well, which I would definitely create if you intend on adding any applications or VMs to the system. If you're not going to add apps, if this is just a pure NAS play where you're going to be writing data over SMB exclusively, fine, you don't need a cache pool for that. You can probably don't need a cache pool for that. There's other caveats to that. But if you're going to run any kind of applications or virtual machines, having an SSD-based cache pool is, to me, a requirement. Like, It's the difference between having a desktop PC with an HDD versus an SSD. It's just that big of a leap in performance change. And if you're just running some basic apps, your cache pool can be pretty small in size. You don't have to go super large. Even just 2 SSDs is fine if you want to keep it cheap and redundant. But yeah, it's going to dramatically increase the performance of applications and VMs. And like for an app like Plex, the metadata mostly lives in that app data folder. And so you don't want to be waiting on spinning disks to pull up box art or whatever else lives in that metadata. And we wouldn't be talking about storage wouldn't be a complete subject if we didn't talk about the controllers themselves. So the key with storage controllers is to get yourself standard HBAs that aren't hardware RAID controllers. Okay, hardware-based RAID controllers create lots of headaches for software RAID solutions, so stay away from them whenever possible, or look to our forum for guides on how to flash them with firmware that turns them into a standard HBA. And just for a second, I'll touch on this. The reason that hardware-based RAID controllers can create a lot of headaches is that when your system is booting up, usually there's an interface you can enter that's kind of like the BIOS, but for the RAID controller, where you configure your RAID group. And even if you're like, you know what, I'm just going to leave all these devices as individual devices, I'm not going to put them in a RAID group. What a lot of RAID controllers do is they malform the UUID of the underlying storage device. So when you attach a storage device to a standard HBA, a standard storage controller, and you boot it up, the unique ID for that device, which is what we use to determine is that disk 1, is that parity, is that disk 3, the way we identify that is by that UUID. And that UUID, when you plug it into a standard SATA controller, is whatever the device's UUID is. It's just the device. When you go through a RAID controller, what happens is the RAID controller is trying to take a physical disk and turn it into a logical one, right? So for example, if I was creating a RAID 5, I'd have a whole bunch of disks attached to this hardware-based RAID controller. I'd tell it to create a RAID 5, and what it would present to the operating system when the software starts to load is a single logical disk. It wouldn't show me all 5 of the individual storage devices. Instead, it would show me this single logical unit, and that's how the operating system would interact with it. And so in a lot of cases, when people use a hardware-based RAID controller and they try to leave all the disks as independent disks and they get Unraid booted up, what ends up happening is where the disk serial number would be in the main tab where you'd go to select them from those dropdowns, you'll see a completely different string that is actually being presented by the RAID controller. And part of the problem with that is that string can change. And it especially can change if, for example, your hardware-based RAID controller were to fail and you got a replacement and now you had to redo all of that. Or if you are switching from that hardware-based RAID controller to, say, a standard SATA controller, upon doing so and booting up, your array is going to say, I don't have any devices because all the UUIDs are different. So hardware-based RAID controllers just make our lives more difficult. So stay away from them wherever possible. Onboard controllers built into the motherboard, they're ideal. They tend to work just fine. This is especially true, again, with Intel-branded devices. I've never had a problem with an Intel-based storage controller built into the motherboard. And something to keep in mind is add-on controllers that you would add as PCIe devices. They can vary in quality, and there's not as many of them available in the market nowadays as there used to be. So all I can say there is just don't go cheap. If you go cheap on a storage controller, an add-on storage controller, that can manifest in the form of performance problems or other compatibility issues like we talked about before with Marvel and IOMMU groups and stuff like that. So don't go cheap and expect high performance results. All right, so going hand in hand with talking about storage, though, we should also talk about the network. So for the vast majority of users that are out there, you're going to have a 1 gigabit network with a handful of wireless devices as well. The main consideration for network with your server is going to be how often you're going to be copying data to it from a Windows or Mac device on the same network, and how many users, right? So the array does a great job of doing one write operation at a time, but when multiple writes from the same or different users are hitting the array all at the same time, you'll quickly see a performance bottleneck. It is for these use cases where the creation of a cache pool can have a dramatic improvement to performance. And for a 1 gigabit network, you can assume that no single user will write to the system at a speed faster than 125 megabytes per second, as that is the max speed a 1 gigabit per second network with no overhead can achieve. Realistically, it's going to be somewhere in the 100 to 110 range, but we're going off straight math here. 8 bits to a byte, do the math, 125. But if you're one of those special people that's out there with a 10 gigabit network, once again, the plot thickens. 10 gig networks can reach speeds of up to 1.1 gigabytes per second in transfer rates. That's real performance that we've seen. But there are a lot of things that have to be in place to make this happen. Both your server and any client devices have to have 10 gig NICs in them. You're going to need a 10 gig switch in between them. You're going to need to make sure that that network is optimally configured for the throughput. In addition, various NICs from different vendors seem to do better or worse jobs at handling this. Specifically, recently, we did some internal testing and saw really great results on Intel. We got about pretty close to 10 gig performance using Intel. But then when we went through a user share as opposed to directly to the cache pool, the speed dropped a little bit and went like to 800 megabits a second. But then we had one of our community developers just absolutely blow the door off with a solid 1.1 gigabytes per second using Mellanox devices. And again, going to really high-end storage performance, but I just don't understand why that made a difference. You would think Intel would be better, but or at least as good, but it wasn't in this case. So we're going to be doing more and more testing with 10 gigabits soon. So just stay tuned for more details on optimizing for that level of performance. But it's definitely possible to saturate a 10 gig link when writing to a cache-enabled user share. You will never get that speed to a hard drive in the array. Hard drives tend to cap out between 150 to 225 megabytes per second. So getting faster than that just isn't really attainable without going to full-blown RAID. All right, so last but not least, I want to talk about the flash device, because this, believe it or not, comes up a lot. We don't have a list of flash devices that we recommend because, again, just like with storage, things change. The general rule of thumb is do not use a generic or off-brand device. Try to stay away from slim profile devices. I used to actually think these would be better because you're less likely to knock them off the back of the case. But we've seen a number of users report heat problems when they use these slim profile devices. Internally mounted is still the way to go if you can. So if you have an internally mountable USB port in the system, the reason that's ideal is that now no one is going to knock it off, right? It's mounted inside. But if you can't, it's not the end of the world to have it sticking out the back. One big rule of thumb is if you got it from a trade show for free, it's probably not a good one. So I would just say, just get one that's 8 gigs or larger. You'd be challenged to find USB sticks smaller than 8 gigs nowadays anyway. I'm sure you can on Amazon, but like you go to Best Buy or something, the lowest you tend to see nowadays is 16. So 8 or larger, you're fine. But that's all we really have to say on Flash. There's not a silver bullet trick to knowing you're going to get a good or a bad Flash. We just tell people stick with quality brands. Don't go bargain shopping for them. Just get something of quality. All right, so to end things for today, I thought I should give you maybe like 3 general ideas of how you could size a system. All right, so let's start with something that's going to be a basic NAS, right? No apps, no VMs, just pure storage. For this kind of a system, I would go with a low-end Intel or AMD CPU. Either a Celeron or Athlon series device would be fine. 4 gigs of RAM, like I said, minimum requirement. Gives you a little room for application adding or plugins. But you don't need a lot of memory for this use case. 1 gig NIC, obviously. And then for the array, I would start with a minimum of 2 to 4 storage devices. 4, I think, is the entry point in my mind. If I'm building a server, if I'm going through this whole process of building a server, I kind of want something that's not just going to handle me for the next month. I want something that's going to handle me for, I don't know, at least a year, and then I can add to it after that. So I would go with 2 to 4 array-based storage devices. And in this use case, I probably wouldn't use a cache pool. That doesn't mean that I wouldn't benefit from it. I could turn the cache pool on and get way better performance. But in that low number of devices, if I'm being honest, what I would probably do is just, if I really wanted to saturate the network or I really wanted to get max performance, I would just let the disks spin all the time, and I'd go to the disk settings page and I'd turn on what's called reconstruct write, and that just makes it so that all the disks spin when write operations are occurring. And as a result, it makes your performance go much faster. So you'll probably max out your network with that configuration. So that's a good low-end example. Now let's shift to a slightly more common use case for a media server. So now here, it does kind of tie back a little bit to Plex's requirements. So Plex will say that if you want to be able to transcode 4K content, right, you're going to need an i7 or better processor. And that only gets more strict if we're talking multi-user. But if we're not talking 4K content, then I would say for somebody who's just getting started, an i5 Intel or even a Ryzen 5 would probably be more than enough. I would go with 8 gigs of RAM for this configuration to give yourself more room for the applications that you're going to add. I'd still stick with a 1 gig NIC. 4 to 6 array-based storage devices is probably a good starting point. And then I would get 2 small SSDs between 128 and 256 gigs in size for your cache pool. So if the cache pool is just going to be used for app data, you don't need very big SSDs for that. You need enough to support the containers that you're going to be running and the app data that they're going to create. But if you're going to be creating VMs as well, that's when your cache pool's got to get sized larger, or you need to build a separate cache pool for it. And we'll talk about that in the next one here, which is Big Bertha. Okay, so for a Big Bertha system, okay, when I call Big Bertha is just any system where you're just throwing money, at it just for the sake of it, like go faster. So for that kind of a system, i7, i9 CPU guaranteed. I would probably go with a minimum of 32 gigs of RAM. 1 gig NIC still. I'm not going to give you a 10 gig NIC build system just yet because the storage required for that and the complexities in that is a lot more to figure out there. I would definitely go with 8 plus storage devices for the array. And I would have 1 to 2 cache pools in the system even. I would have 1 small cache pool with 2 128 gig, say, SSDs. And then I'd have 2 1 terabyte SSDs that I would put in a RAID 1 cache pool for my VMs so that they have redundancy as well. So that is, a pretty decent spec system. You could go even bigger. You can go 64. You can go, hell, some systems you can do 128 gigs of RAM. It really comes down to how many other apps and whatnot that you're going to be running on the system. So, but this system that I'm speccing out here, this Big Bertha, you could easily throw a graphics card in it. And by the way, if you're going to get a graphics card for gaming, right? And we're not talking AMD versus Intel anymore. I'm talking about how to size that, right? We talked earlier about, you got to look at the games. Generally speaking, if I'm buying a graphics card today for a new build today, I'm not getting anything less than an RTX. And I probably at this point wouldn't go less than a 30 series. And the only reason is that everything, like RTX is a new technology, right? Ray tracing is a new thing that they're doing. And when a new tech like that comes out, the first several iterations of it, there are monumental jumps in performance as they get better and better and better. It's kind of like when mobile smartphones first came out, they had a base set of capabilities and they were okay. They were better than the flip phones of old, but they were slow, they were clunky, they didn't have the smoothest interfaces. And year after year, like 1 year at a time, you saw monumental leaps. Now look at the last 4 years of new phones that have come out. And yes, they're still getting better, but the percentage better that they are from their previous year version is not as big as it was, back in the early 2000s, mid 2000s or whatever. So similar rule kind of applies with graphics, in my opinion, is when new technology like ray tracing comes out. RTX 20 series was its entry. Now the 30 series is where we're seeing the first big leap in performance, and whatever the next generation of NVIDIA device is going to see, we're going to see another jump in performance, but it might not be as big as it was from 20 to 30. Not sure yet. Got to wait and see. But I would definitely lean more towards the RTX 30 series. And I personally think ray tracing looks really cool. I'm going to be a lot more excited about it when more games support it and when we can do it at over 120 frames consistently with high quality graphics for everything else, because I'm a snob. I'm a gaming snob. So, all right. Well, I think that about wraps it up for the first episode about hardware. If you guys have additional questions for me about hardware requirements on Unraid, please feel free to leave them in the comments below or post on our forum. Definitely eager to hear feedback from you guys. And if I need to drill deeper on any of these subjects, or if you want me to do deep dives on performance requirements for specific applications, or you want me to do a deep dive on Plex and transcoding, just let me know, because I'm looking for people to give us some feedback on what they want future episodes to be about. So please contribute to the conversation. All right, guys. Well, that wraps it up for today. I appreciate everyone from tuning in. We'll catch you back in about 2 weeks. We'll have another episode for you coming to you soon.